Okay, my friends. So, just so you know, there's been quite a few of you over the past couple of weeks, which is great, that have come in and earned points back. And it's usually half points, but every now and then, bless you, there will be a valid argument that I will get from you on a question where I'll give you the full point back. Laura, I think what did I get? 2 points that you had about 3 points that was a valid argument that like the question because of how it was phrased. It's always interesting to hear, like how you would have conveyed a question, and then it's like, oh, I understand that, and so it really is worth your time to come in and earn at least half the points back, if not more. And I'm happy to do it. And again, I told you guys a little bit, me and Mr. Anderson teach the class. He curves his test dramatically. I like the fact that you can get half points back with me because I think it reinforces your learning. And that's why I do it the way I do it, and he does the way he does it. Not that he's wrong and I'm right. It's just one way works better for me, and one way works better for him, and that's fine. That's just kind of how, classes go. So I think I have attendance good so far. All right, I'm on page 29, so we're starting chapter 2 today. And the nice thing is scatter plots are going to work with Desmos very well. So that's kind of cool. Get my coffee. All right. So we're talking about, again, on page 29, we're talking about scatter plots. Okay, this is where we have two quantitative variables presented as coordinates, x and y values. Okay, so we make points. And then the main purpose of a scatter plot is it's very possible that you could collect two pieces of data, bless you, and you could see a trend. And a lot of times a trend, it could be linear. It doesn't have to be linear. Obviously, the more points that you create, if there is a trend to it, the more and more obvious it becomes. So if we were to do, and I'm not going to do this, but if we were to take, say, like, if everyone were to measure their hand, their spread out hand from the tip of their pinky to the tip of their thumb, and then the height in inches, if we plotted one on the x-axis, one on the y-axis, created points out of it, we would actually have a linear trend to it. Now, it is possible that you might have outliers that do exist. So if you had data that kind of plots in and looks something like this, but let's say you have that one here, what would that red circle point be in your verbiage? What would that be known as? And it's an outlier. Yeah. Okay. So you could have an outlier, and as far as outliers go, we don't get rid of outliers. We could, if we plotted our data, we could look at an outlier to make sure we put in the right data point, but it is possible that our data point is correct and it truly is an outlier. But there could be times, especially now that when you're plugging in data, it is possible that you might transpose your x and y values. So when you're doing these types of things, yes, you should investigate an outlier because it is possible you might have flip-flopped the points, or you realize, Cindy, and I'm just making up a person's name, Cindy accidentally gave her measurements of her hand to her height backwards. Okay, and that's things that we could then correct it. we can't just go and eliminate an outlier. We can investigate it, and it is possible that it truly is an outlier for whatever reason, not because somebody's broken. So this is the horizontal axis. And the horizontal axis are called our explanatory variables. And then the y-axis is called the vertical. And the vertical are our response variables. And sometimes it's kind of hard to decipher why something would be explanatory versus response, especially if you're doing, two measurements of your body, the distance from your pinky to your thumb and your height. Would the height dictate the size of your hands, or would your hands dictate your height, or would your height dictate your hand? And it kind of is goofy to think about, things are going back and forth. Sometimes these are called the dependent variables. And then these are sometimes called the independent variables. And things like that. So things that you could do, when you're comparing things, especially for college, you could look at your GPA and say an ACT score. Normally, you might have a high GPA and a high ACT score. But it's also possible that you might have a really high GPA and your ACT scores aren't what they should have been, but the ACT, sometimes students don't do as well on a standardized test as they would do academically in the classroom. Sometimes they would. Because you do well in the ACT doesn't mean you're an unbelievable student. Because you do well in school doesn't mean you're a good test taker. Okay. And especially when you have courses like mine, where you could go and you could improve your grades by coming in and seeing me and going through in just a couple minute discussion, which is fine. So here, a hypothetical piece of data on the bottom, page 29. You could talk about the amount of crime that occurs versus the amount of unemployment. Does crime go up when unemployment's up? Sure. But there's other things that could take place with, there are some areas of different cities or different states that might have a higher crime area, but have a high employment rate. And it just really depends, sometimes where you live. All right. So on page 30, we start talking about data that goes all over the place. And so picture 1 and picture 5 are just kind of all over the place. There's really no rhyme or reason to the dots. They just go all over the place. And then if I look at 2 versus 6, 2 is kind of all over the place, but it looks like it has some sort of linear trend in the positive direction. This would be positive. This has a linear trend to be in the negative. When I say a positive trend versus a negative trend, that just means that the slope of the line is positive versus negative. And then if you look at 3 and 7, these are a little closer together. So these both have positive or negative trends to them. And then if you looked at 4 and 8, you might have a really strong positive, or you might have a really strong negative trend. Okay? And things that could give you very strong pieces of data, a very simple thing. The big Gatorade jugs, or the water coolers that you push a button and you can fill up your water bottle. If you were to just hold that and have a timepiece, and you start time and you hit the button at the same time, as that water goes down versus time is a very strong negative correlation. Negative not meaning bad, negative just means the slope would be negative. So there are some things that you can definitely get some really good data off of just by looking at it. So the positive and negatives mean you're talking about the slope. Oops. So if you saw something that had a strong positive, this would mean my slope of my line is rising to the right. Yeah, negative slope, the slope of my line is falling to the right. Okay, and again, positive and negative doesn't mean good versus bad. It just means that's what our data is doing as we head out towards the right. Is it going further away from the origin or from the axis, the x-axis, or is it coming closer to it? So positive association versus negative association. And then we can also talk about, we have strong correlation, and this is close to a straight line. And we can have weak, and this is kind of scattered data, and then scattered data could have somewhat of a line that you could say this line would probably fit in. And in science class, you probably have plotted data and you have to pick two different data points and create a line of best fit. Desmos will do that for us, so that's kind of a few things. So on 31 it says, be aware, scatter plots collected from data can look just about like anything you dream up. Consider the following scatter plots. So they have one that kind of is all over the place as you go further to the right and up, but it's closer together as it's down closer to the origin. There's all kinds of things, but there are values that we will talk about. We're going to talk about the R and the R squared value. And the R value is a linear representation. So if you're at -1, means I have a negative slope. If I'm at +1, means I have a positive slope. Okay, and you can have anything in between. If you have something that's close to 0, 0 is very weak. Okay, as far as your data. 0 means your correlation, the linear correlation, a one-dimensional representation of your data is all over the place. R squared is literally R times R, going with your algebra. R squared is a two-dimension representation. Okay, what that means is this. So if I looked at my R value, if I had plotted data, in order to get my R value, I'm going to take the average vertical distance. So the R is the average vertical distance. To get it, okay? And it's a huge equation. Fortunately, Desmos will do it for us. If I were to do R squared, it's the vertical and the horizontal. You're creating these boxes from your data, and you basically take the area of each of your boxes. That would go with this. R squared is always positive. It's always a positive number, because if I were to take two negative numbers and multiply them together, think back to algebra 1, we get a positive number. Okay, and again, your things that we do will work. So let's take some made-up data and plug it into Desmos and see how Desmos deals with this. All right. Decimals. Graphing calculator. So you're going to hit your plus button and you're going to go to a table. Now, I'm just going to make up some data. Let's say I went around the room and asked about your shoe size versus your height in inches, and we had all the females. Let's see. I can't remember what it is. Let's say we measured everybody in the same, just as men's. Let's say I'm just plugging in some data. Let's see, size 8, 56, size 7, 54, and size 8.5. Let's go with 62. Okay, so what we can do is we can go find this data. It should have it plotted. There it is. So that's my data plotted. Does it appear that there's some sort of straight line that might work with that? Yeah, I mean, obviously if we collect more and more data, we might get more and more of a trend. Like we could go around and find, ask everyone their shoe size and ask everyone their height in inches, and we would be able to see probably some sort of correlation. Typically, people who are taller will have larger feet. It doesn't mean if you have large feet that you are tall. You could be an outlier. You could be one of those people has a size 13 feet and you're 5'5". You do that. All right, so let's see if I can remember this. Okay, so if I wanted to get my line of best fit, I'm going to go y_1, and I'm going to use the tilde command. I just have to remember where tilde is at. It's just shift up here of mx, mx, I believe I'm doing this right, plus b, plus b. I think that works. Nope. Oh, there's my mistake. There we go. So if you plug that in, notice my list is x1 and y1. So I use y sub 1. I use the tilde because tilde will tell the graphing calculator or Desmos that you want to figure out the equation, m being slope. We remember that from algebra 1, I hope. And then x sub 1. And it's x sub 1 because our x values are x sub 1. And then plus b. And you'll notice that when I take a look at it, it gives us an r squared value, gives us an r value. It gives us a slope of 2.4, and it gives us a y-intercept of 37, or 37.8. Okay, so the y-intercept means if you have a size 0 foot, you would be 37 or 37.8 inches tall according to our information. And of course, if I darken this a little bit, it makes it a little easier to see. We're not too worried about residual values. Residual values are just how far things are from our line of best fit. But the line of best fit is done very quickly. So if you wanted to make your equation, you would go y equals 2.4x plus 37.8. Okay, and then you could make predictions based on our data. You could say, well, how big would someone's foot be if they were, 58 inches tall? And then we could solve, plug 58 in for y, and solve it algebraically, and it would tell us, so we could get some different information from it. But Desmos works really nicely. Things to remember is don't do y equals. It's the tilde that takes place in order for us to get our operation to take place. And we don't have to just create linear models off this. We could create quadratics. We could create third degree polynomials, which has a little, could have a bounce, a wiggle, and a cross. We get a fourth degree, fifth degree, but as far as what today offers, we just have linear components. Okay, so Desmos is a good thing. So let me just, sum up on Desmos. Make sure you know how to do it. So for Desmos, you're going to hit the plus, and this will give us a table, make a table, and we'll plug in our x1 and our y1 values. And then once your values are fine, find where it is on your graph. Find on graph. And then you go y1 tilde mx1 plus b, and it'll give us the r and the r squared. It'll give us the slope, and it'll give us the y-intercept. And yeah, so have a seat. Instead of the company seat at once. What's the lesson? First one? Is that the only one you're on here? There's a good one. Okay, cool. Let's do that one first. Perfect. All right. So what do we have as far as an assignment goes? All right, so I'm going to give you the opportunity to work on page 135 and 136. And I'm happy to help you on any of those. Should be pretty good to go. It looks like you can plug your data into Desmos. On the very first one where it says high temperature, I'd say high temperature would be your X value. Number of visitors would be your Y value. Cool? Need